Yeah, good afternoon everyone. So I am not going to deal with all the parameters and performance metrics for classification. I am just reviewing that and I want to go to the next concept. Yes, I think yesterday we covered this concept, performance metrics for classification. First of all, what do you understand about the classification? What do you understand about the machine learning algorithms? First step. The machine learning algorithms, we can classify them into various categories: supervised, unsupervised, and then semi-supervised and reinforcement. Okay. So what is the supervised? Supervised means labels are given, meaning that for the existing data we have the input as well as the output also, output values also available. So that is a labeled data. Labeled data in the sense output is also available, that is target is also available for the old data. Our job is we have to build a model based on the existing data, we have to predict the new values, meaning that new targets for the given inputs. That is the supervised. Unsupervised means we don't have the labeled data and based on the similarities in the data points we have to group them. That is called the unsupervised, meaning that if we don't have the labeled data then we will go for the unsupervised learning. Okay. And then semi-supervised. What is the example for semi-supervised? Anybody can tell? Semi-supervised. Semi-supervised. I think all of you are using Facebook. You are using Facebook, right? And in Facebook or Google Photos, if you move the pointer to the face, it will give you the name of the person. Or it may prompt who is this. Did you see that? In the Facebook, if you open the photos, if you move the pointer, mouse pointer to a face, it will prompt you either who is this or it may give the value. Meaning that is the, that is called the Google Photos. Actually it is the Google Photos concept. Facebook has also implemented this. Meaning that some faces they have the labels, for some faces they don't have the labels. Meaning that the labeled data and unlabeled data both are available in that data set. That is called the semi-supervised. For half of the data there is the label and some other data it is not labeled. So in such case what to implement, what kind of algorithms we have to implement, that comes under the semi-supervised. Generally we will take the supervised learning first, unknown values and unknown labels, and then we can apply the same supervised learning. So these are the several techniques available in that. So you may get this question, what is the semi-supervised? Example for the semi-supervised, generally it is the Google Photos, Google Photo identification. This is the example for that. Okay. And then reinforcement. Reinforcement means, what is the reinforcement? Trial and error. There is no predefined data or anything. Start working on the data, whatever is available, whatever is coming, and based on that we will learn. Example, the general example for the reinforcement learning is the cycle learning. How you learn cycle? How to write cycle? How you learn? Anybody teaches that you have to apply this pressure on this right pedal and then left pedal and then again push the left pedal. Anybody has given this theory? And you have to, your handle should be with 90 degrees and you have to turn 30 degrees to left turn and right turn 30 degrees, 45 degrees. Anybody has given that? No. How you learn? You start. Even if you don't know, you start riding the cycle. Sometimes you may fall down or you may meet the accident or anything, right? So that you will learn by experience. That is a reinforcement. So number of times if you do the same work, you will get it, definitely. Accuracy will be increased. So that is the reinforcement learning. So in that, the classification, we discussed about the regression and classification. We concentrated on the supervised learning only, meaning that data is available with labels. So again in the supervised learning, we have the two concepts, regression and classification. In the regression, we are having the simple linear regression, multiple regression and polynomial regression. Simple regression means your correlation. Already Yunus sir discussed about that. The relation between the two attributes, and we can fit a line, and how to do that least squares method is also completed. That is a regression concept. And classification is another way. Already we discussed about that. There is a categories. If your target is category, not the value, then we can go for the classification. Now, for any model, you can design any model, there should be some metrics, some units to measure whether it is properly fitted or not, the model is properly working or not. To identify that, we should use some metrics. So for the regression, there are some metrics. For classification also, we have some metrics. Regression metrics, yesterday we discussed about them. MAE, mean absolute error, mean squared error, root mean squared error. Okay, the predicted value minus original value. The predicted value minus original value, either it is plus or minus, we have to take the plus only. Error is either plus or minus, error is error. So that's why we have to take the mod of the difference between the predicted and actual values. So this is what we have done. The mean absolute error and mean squared error also we identified. And then classification. If you come to the classification, again there are some performance measures. They are the metrics for classification. Already we discussed about this also, we covered, that is the confusion matrix. The confusion matrix will give you the metrics for the classification. So see here, I don't want to discuss all these things. See here, this is the linearly separable, okay? This is a linearly separable. So this is a linear classifier. There are so many linear classifiers. One of the linear classifier is the logistic regression that you have done yesterday, you have executed that. Okay, if you are able to separate the two categories with a line, then it comes under the linear classification, linearly separable. And sometimes you may not be able to classify them, okay, meaning that these blue dots may be here, these red dots may be here. In such case, what can we do? If we increase the dimension, see it is like this. If you increase the dimension, if you make it like this, if you are seeing from here, you may not be able to classify, meaning that I will give you a small example here. I will show you this. See here, these two are there. See, these are the two types of objects. If these two, from your view, these two are having same, in the same class. But if you change the dimension, you are able to classify, right? So if you increase the dimensions, automatically you will be able to classify that. So if you increase the dimensions, you can classify. And that concept is again, it is a different concept, that is the kernels. We will use the different kinds of kernels. Linear, this is the linear classifier. And if you take this is the linear, and of course, you can, this is the logistic regression concept. After that, if you want to go to the next level, there are some other classification techniques also available, KNN, K nearest neighbors. Yesterday you have calculated that. Linear, logistic regression, all these are the parametric. Okay, KNN is the non-parametric, decision tree is also non-parametric. Whatever you use, the parametric, non-parametric, the classification is the same. The final result is, it is giving some predicted classes. So for that, we have to identify whether the class is properly predicted or not. For that, the metrics are common for all types of classifications. For any regression you can use, the metrics are common. Regression metrics, classification metrics, that's it. So only to clear the doubts and to clarify this only I am taking this. Now here of course binary classification and multi-class classification may be there. If there are more classes, then how can we classify that? Again there are the techniques here. See here. So see here, we are taking the binary classification metrics. Now in this we are taking the binary classification, we are having some actual values like this. Based on that we want to predict. See here, our predictions are like this. Actually these are the classes available. You can see that these are the classes. See how many? 1, 2, 3, 4, 5, 6, 7, almost 8 and 5, right? And then the predictions are 0, 0, 0, 1, 1, 1, 1 and then 0, 0, 1, 1. So the predictions and the actual values, these are little different. Now based on that construction of the confusion matrix, how the confusion matrix is there? See here, predicted and actual class and predicted class. Cat is classified, actually it is the cat and predicted as cat. How many classified? That is a number. Cat is classified as the cat. And then 2. What is this 2? Actually it is the dog, predicted as cat. It is wrong prediction. And actually it is the cat, predicted as dog. It is a wrong prediction. And this is, actually it is the dog, predicted as dog. So see here, you can see that here, this classification. This I will show you in the different way also. I will show you with the program. See here, this is true positive, false negative, false positive, true negative. See here, true positive, true negative, these two are the correct. And here, see here, this is the total. What is the total actual values? So if you take the actual values here, this is the total actual positive, actual negative. So total how many values are there? Total how many points are there? That is p plus n. And p dash and n dash, these are the predicted. What are the total predicted as positive? And yes or no, how many predicted, total predictions. So based on this we have some metrics. Now see here, this is the same, similar to that. Actual is this and predicted is this. And if you have the confusion matrix directly, skLn, in the skLn matrix we have the confusion matrix module. Okay, in that we are taking the actual and predicted, we are just building the confusion matrix. And you have to understand this, 4 predicted properly, here 3 is also predicted properly, the errors are 3. Total how many? How many values are there? How many values are there? Don't count there, here you have. You have here. Total how many? Here? Total is 10. Right? Total values here only. In these 10, 4 plus 3, 7 predicted properly and 3 errors. And class wise, if you want to see the class wise, how many 0th class are classified wrong? 2. And how many classified in this class? That is 1. So meaning that based on the confusion matrix we can analyze what are the errors and what are the proper predictions, right? And see here, see this. This is true positive, this is false negative. I think it is overlapping, it will destroy all because after downloading the formats are changed. Okay, so this is the true positive, this is actually positive, predicted as negative. So false negative, it is predicted as negative but false. And next one, actual 0, actually negative, predicted as negative. So true negative. And true positive, true negative, true negative, true positive, and false positive, false positive. it is predicted as positive, but it is false, and actually it is false. So, and you can just fill. How many are there? You have to calculate them. Count. 1, 2, 3. 3 are the true positive, and false negative you have to count and you have to fill that. You have to fill. That's it. Okay. And then true negative, false positive. How many are there? We can just fill them so that you will get the confusion matrix. So based on the confusion matrix, see here. And then based on the confusion matrix, we can go with, if there are 3 categories. If there are 3 categories, this is the confusion matrix. How many categories are there? The dimension will be like that. If there are 3 categories, 3 by 3. 4 categories, 4 by 4. So the same thing. 2 is predicted as 0, 0 is predicted as 0. So you have to count them. 2, 0, and then 2, 0. 2 are available. So like that, you have to predict that. Now see here, all these are the same. These are the actual values, these are the predicted values. We are taking, now I think this is the correct way. Yeah. Now you can observe, 2, 0, 1, 2 is predicted as 0, and here also 2 is predicted as 0. Anything is there? Anything else is there? 2 is predicted as 0. 2 is predicted as 0. 2, 1, 1, 2. Okay. And 0 predicted as 0. How many are there? 1, 2, 3. 1, 1, 1. That is 3. So this is construction of the confusion matrix. Okay. Why we are giving this is, you may get a question because the machine learning basics are asked. So you may get a question that you may get actual and predicted values, and you may be asked for constructing the confusion matrix. So you should be able to do this. That's why I am just explaining. Okay. And then accuracy. How to get the accuracy? Accuracy means in all the points, how many predicted as positive, meaning the true positive, true negative, the correct predictions. What is the rate of correct predictions over all the points? So what is that? Diagonal. Diagonals are proper predictions. So we have to take the sum of all the diagonal elements. Right? So what is that? If you take the 2 by 2 matrix only, true positive and false positive. Right? That we have to, yes. True negative, sorry. True positive and true negative. The negative is predicted as negative only. So that is true negative. True positive, true negative, we have to add divided by total number of elements. Total means all the points, all the values in the matrix. So you will get the accuracy. Right? And then recall. Recall means only we will take the true positive over true positive and false negative. What is the true positive? True positive is correctly predicted, and false negative. What is the false negative? False negative means, what is the false negative? Actually it is positive, but predicted as negative. Actually it is positive, predicted as negative. So false negative. So what it is showing? True positive rate over number of positives, actual positives. Number of overall actual positives. Okay, that is called recall. And we have another point, precision. True positive by true positive over true positive plus false positive. True positive plus false positive. False positive means predicted as positive. So meaning that what is that? What is the in the matrix? true positive plus false positive, meaning that negative. It is taking the total, no, true positive plus false, predicted as positive. What are the predicted as positive over true positive plus false positive? False positive ఉంటుంది. Where is that false positive? False positive is on this side. Actually it is predicted as positive, but it is false. So overall positive predictions. Overall positive predictions. How many are positive predicted? Overall all the positive predictions. Right? Now that is the precision. And F1 score. F1 score, precision into recall by precision plus recall, that is 2 into. So here F1 score, you may get this also, F1 score. You may get the F1 score, and which is the best? 1. If you get the F1 score 1, then we can conclude that it is the best fit. And close to 1. 1 means best, 0 is, it is the worst. And if you have 0.8, F1 score is 0.8. 0.8. Is it good or bad? Good. 0.4. We can consider that it is not a good model. So for that we can have, all these are the confusion matrix and all these are given. So see this, for this confusion matrix, directly confusion matrix is there, we need not calculate all of them, we have the predefined methods. Accuracy score is there, and then classification report, it will give you all the scores. What is the precision, what is the recall, what is the accuracy, everything will be given, F1 score, everything will be given. So see here, this is the precision, this is the recall. See here, we are taking this all negative. All the predictions are reverse. So in this case, all are 0. All zeros. And support. Support means each class. Support means each class how many are available? Men 2, women 3, 2. So total 4. 4 data points are there. So support, so where the support will help you? Yeah, this is important point. What is the importance of the support? What you can take? Meaning that it is balanced or imbalanced data set. It will give you balanced or imbalanced. If you have 500 man data set and only 20 woman data set, then it is imbalanced. If you fit a model on that, you cannot predict properly. So imbalanced data set, how to handle the imbalanced data set, this is also another point, another research area. Again there are several techniques are there. How can we use? I will give you small examples. See, if you have 500 and 20 only, 500 in one class, 20 in one class. In such case, what you can take is 20-20 or 20-30. 20-30, remaining you have to leave. In this case, you are losing some data. You are losing some data. Otherwise, another option is you repeat this 20. You repeat this 20 to reach that level, so that it will be balanced and you can predict. And there is a danger of overfit. There is a danger of overfit. So because of that, of course, in the machine learning, for every solution again there are some problems. There are so many problems and so many solutions. For every solution again it will lead to another problem. So here again we may get the, okay. So in your data set directly, if it is having the balanced, then you need not worry about that. Okay. And of course all these are the things. And see here, this is also the 50%. See here, confusion matrix. If you see the confusion matrix, you should be able to understand whether it is a good model or bad model. See the confusion matrix. 1, 1, 1, 1. Total 4 only. Meaning that accuracy is, you need not calculate much, 50%. Total 4, 2 predicted correctly, 2 wrong predictions. Okay. And then support 2, 2 only. And then, now you see this. All men only. All the men. There is no woman. Meaning that only 1. Accuracy is 1 automatically. Reverse is also same. Okay. So, and then we are taking different scores, and this is the Titanic data set. Actually, before this class, we have completed the Titanic data set classification, but we have not done here. Okay. Before this class, we have done that. Okay. So, this is about the classification, confusion matrix, and to understand the classification metrics. So, I don't want to drag more. Now, gradient descent, this is important here. Now, we have already discussed yesterday. In the yesterday's discussion, I have told you that the estimation of the parameters. The estimation of the parameters, already morning you have done one method, that is least squares method. You have done the least squares method, right? In the similar way, this is the completely formula based. It is completely based on the formula. Is it the formula or not? Least squares method. Multiple regression, for multiple regression also there is the solution for that. And here the gradient descent is another method to estimate the parameters. Okay. There is no guarantee that everything will be having the formulas. So, we will take the random values for the weights. Yesterday I explained this outline, right? Actually, we didn't expect that today we will get 1 hour. So, that is why I just want to elaborate this. Okay. Now, so see here, okay, this is not that. Gradient descent. Gradient descent means we have to discuss about 3 parts. Okay. Batch gradient, stochastic gradient, and mini batch. These are the three types of gradient descents. Okay. Let us discuss step by step. So, see here. What is this graph? This is the cost. This is the cost function, meaning that loss. We will call it as the loss. If you take the regression concept, in the regression you can understand very nicely this. Instead of the classification, regression you can understand, and you can apply the same thing on the classification also. In the regression, the mean squared error. So, see here, this is the cost, and what is this? Steps. If you increase the steps, then see here, this is our cost. If you increase the steps, number of steps, if you increase the number of steps, meaning that next, if you are going step by step, our cost should be down, our cost should be low. Okay. But here, if you see this curve, this is the total data. This is the total data. In this, which is having the lowest error? Cost means error only. So, which is having, this is the point actually, right? If you take the global data, then it is the minimum. And here, we will start here and we will travel. When you reach here, we will stop, because we will think that the curve is like this, right? If you are interested in the trekking and mountains, so in that you may be able to understand this, meaning that if we reach one place, we will feel that yes, this is the top position. Later there may be some more point. So, see here, we will stop here only, and this is called the, if you take this data And one more thing, we cannot take the entire data also. Another important point, we cannot take entire data. We will take the sample for training the data, right? To train the model, not the data, to train the model. So in that, whatever we have taken the sample, if you take this sample only, we will fix here only. But in the original data, the original point may be here. So local minima, this is called the global minima and local minima. Global minima means on the entire data, what is the lowest cost point, and local minima in the taken sample, what is the minimum cost. Okay. And now see here how we will go. See here, we will go up to here and again we will be back. Okay. Now you see this is the predictions, based on the predictions. Based on the predictions, meaning that step by step data points, we are considering this. So if you are using this, actually this is very good in the stochastic gradient descent, I will explain that. So see here. Now in this, if you are here in the gradient descent concept, the main aim is to reduce the cost, meaning that the error has to be reduced. According to this, we have to update the weights. Our aim is the cost and our tuning parameter is the original parameters, that is beta 0, beta 1, beta 2, beta 3. We have to change them. How can we change them? That you will not find here. Yes, see here. Here the new weight, that is I want to update the weight, beta 0, new weight means you take that as beta 1. Our equation is, let us take the equation beta 0 plus beta 1 x. Beta 1, this is the beta 1. I want to update the beta 1. Existing weight, that is initially we will take the random value in the beta 1. That random value, whatever you have taken the random value, minus learning rate into gradient. The gradient means, just now we are discussing, the gradient means it is the error, okay, which we have calculated just now into learning rate. How much you have to change based on the error, how much you have to change. That is called the error rate, learning rate. Based on the learning rate, you will take the steps. So you are here. If the learning rate is small, then the step will be very small. If the learning rate is high, then the step will be very large. You may miss the minima at that place. So you see this here. We are starting here. This is the initial weight. What we have taken. We will calculate the gradient, that is the differentiation based on the first order derivative, and we will find that gradient, and then based on that we will take the learning rate. Based on the learning rate into the gradient, we will change the weight. The weight may be coming here. And then again we will apply. Again we will find the gradient. Again we will find the gradient and again we will apply that, and so on. Finally we will reach the lowest cost. We have to reach that. So every time what should you do? Take the initialize the parameter, that is the beta 1, and then proceed with all the data points, and then find the loss, calculate the loss, and find the gradient for that, that is the derivative, and multiply that derivative with the learning rate, and you have to take the previous weight minus learning rate into that gradient. So you are updating the beta 1 with the old beta 1 and the gradient. So the gradient is playing the important role and the learning rate is also playing the important role. These two are very important here. The gradient calculation, it is easy, not a big deal. If you are good in the derivatives, first order derivatives, second order derivatives like that, then you can easily find this, not an issue. Okay, but the learning rate is playing very important role. How much we have to take the learning rate? It is playing the role. Now, see this. Okay, see here. Big learning rate, if you take the big learning rate, see this. This is the lowest cost, right? And if you take the big learning rate, we started here and our learning rate is high. So the next updated value is giving here. The next updated value of the beta 1, it is giving this error. And then next value it is giving here and it is giving here and it is going up. So what is our intention? Our intention is to minimize the cost, but what it is doing? It is increasing, right? But if you take the small learning rate, to reach from here to here, it is taking so much of time. So many steps will be taken. So many steps will be taken. So both are difficult. I will give you a small example in our steps. If you want to go down, if you take one by one steps, or every step you are taking 2 steps with your legs, then it will take so much of time to get down. And if you take the 4 steps, if you cross 4 steps at a time, then what will happen? You will fall down, definitely. Same here also. If you take only single step, not even single step, 0.5 steps, then it will take long time to reach the goal. So small learning rate is the problem and big learning rate is also another problem. So we have to take the optimum number. What is that? How can we take that? Are you getting? Am I with you? Okay. So here what we have to take? First we have to take the initial values of the parameter. Next apply our function, that is hypothesis. After that finally we have to calculate the loss and we have to calculate the gradient for that and then update the weight beta 1 and then proceed this and then continue this process. Continue this process is called the epoch. This is called epoch, right? Now see here, theta means the parameter, any parameter. Theta equal to theta minus alpha. Alpha is, what is alpha? Learning rate. Alpha is the learning rate. What is this symbol? Dou. Dou by J of theta. What is J of theta? J is the loss or cost function or loss. Okay, meaning that we are finding the derivative of loss with respect to theta. Please remember this. This equation is very important. See here, we are finding the derivative of the loss function with respect to theta. And we are finding that and multiplying with the learning rate and subtract from our current weight or current value of the beta 1. And we are updating this. And we have to continue this. Now, come to this point. Gradient descent means if you have 5,000 records, please remember, if you have 5,000 records, all the 5,000 records will be evaluated and then, meaning that not evaluated, they will be processed and then evaluated for the cost and it will find the cost. If you have 5,000 records, 5,000 records will go through the model without changing any parameter, without modification of the parameter, with the random value, initial value only, all these 5,000 records will be processed and then we will calculate the loss or cost. So this is the problem actually. If you have very large data sets, let us take in the deep learning algorithms and in the higher level machine learning algorithms, we will take the millions of records and billions of records. If we take millions or billions of records for one epoch, it will take long time. So what will be happen? The total process will be very slow. The training will be very slow. If you have 10 records, okay. If you have 100, okay. 5,000, okay. Even 1 lakh records also it is okay, acceptable. But millions, billions of records, and even the records also you have to consider another thing. Yes, listen. You have to consider another thing also. Even if you have 1,000 records, each record is having 5,000 parameters, then again it will be the problem. So in this case, if you go with all the records in one go, then it will become very slow. So how can we solve this? Mini batch. It is a batch. Actually we will not call it batch. It is a vanilla of gradient descent. Okay. Batch means we will take some batches, meaning that in the 1,000 records we will take 500 records and then 500 records. 2 batches. We will go with 2 batches, and in the one single epoch, first it will take the 500 records, calculate the loss, and then update the weights and apply the updated weights on the next records and then come back. So in the single epoch we are changing the weights 2 times. If you take 100 as the batch, how many times the weights will be updated? 100 as the batch, total 1,000 records, 100 is the batch. How many times the weights will be updated? 10 times it will be updated. So within the one epoch only, we will get a good value for the weight. And if you go for the number of epochs, so meaning that if you apply the batch learning, in the batch of gradient descent, mini batch, we can call it as the mini batch. Okay, batch gradient descent, we can reduce the number of epochs because in each epoch it will update number of times. Hope you are getting. And there is a stochastic gradient descent is also there. Stochastic is, yes, this is very important point. Gradient descent is all the records will be considered, and the batch means it will take some batches, and stochastic gradient descent is it will take one record. For every record if you are updating the weights, that is called the stochastic gradient descent. Is it beneficial or problem? Stochastic. For every record, for every point it will update the weight. Is it correct? Every time it will change. But is it suggestible? For every record it is updating me.
Yes, sir. Instead of calculating the error for the entire system, you are updating frequently.
Yes. If there is some fluctuations in the data, then no, fluctuations in the sense data set itself is having. The data itself is having. I am not talking about the problems in the data. The data itself is like that.
We'll have some.
But it will take again more time. More time also. Every time we have to calculate. So instead of taking the batch or stochastic with every instance, we will take the mini batches. Always the mini batches will give you the good result. Meaning that instead of taking 1, 1, 1, 1, I will give you a small example. In this I want to evaluate all of you. Okay, I want to give the summary of the class students. If I take 1 by 1 interview, then it will take so much of time. If I take all of them, I ask one question and based on the answer, if I give the summary, then it is also not correct. So I will take the batches. This batch, this batch, this batch, 5 questions I can give so that I can get the correct analysis. So mini batch is suggestible. Stochastic and vanilla gradient, these two will give some problems, and mini batch is the suggestible. Okay, now see here, learning rate is also, now learning rate is playing important role as we discussed, learning rate. Now how to fix that learning rate, which is the small or big, what should we fix? Generally the learning rate will be, we have given this 0.1, 0.01, 0.001 like this we will give in general, and batch sizes also, usually we will give the batch sizes also like 64, 128, 255 like this we will give the batch sizes also in general. 2 power. And this learning rate, the fixing of this learning rate is important point here. To fix that, there are several optimizer techniques. We will get so many optimizers to fix this learning rate only. To decide what is the learning rate. So we can maintain the same, we will take the fixed learning rate and we can maintain the entire process. That is one way, that is what we are following here. But based on the performance while training, if you are able to tune that parameter, if you are able to tune that learning rate, then it will be a good idea. Meaning that sometimes in the starting the learning rate may be very big and later on you have to reduce the learning rate because you have to get the correct output, meaning that it should be fast as well as it should be accurate. The accuracy should not be affected and the fast is also should not be reduced. So the performance. So for that there are several optimizers available. So there are several optimizers like, see here how learning rate is affecting. See, if you take the low learning rate, for the number of epochs, the loss is reducing based on the number of epochs like this. Okay, and high learning rate, for high learning rate, the loss is reducing for the small number of epochs, but it is fixed at one loss point. So it is not getting the minima, local minima properly. And if it is very high learning rate, it is going away. See this. Don't give the high learning rate, and a good learning rate, it will give you like this, reasonably. So that to find that good learning rate, we have to go with different methods, that is ADAM, RMS prop, ADAGRAD, RMS prop, ADAM, all these are the various optimizers. The optimizers will play the important role to tune this parameter. The gradient descent concept is same, but based on this optimizers, the tuning parameter, that is the learning rate, will be modified. Right? So these are the various things. Generally these parameters, these optimizers, we will use in the deep learning concepts. Generally for the regular machine learning concepts we will not use. Right? I hope I have given some sufficient stuff for the gradient descent to attempt the interview, not interview, for the test first round, and you can talk something in the interview also related to this. And now one more point. Here we are talking about, actually I stopped in the middle of the discussion. We have the linear classifiers and we have some problems of misclassification and where we have to fix that classifier, where we have to fit that classifier, that line, that is also playing important role. Okay, I will just open the diagram and I will try to cover that. Yes, you just see this. See this diagram. See this diagram. I am just giving you the introduction to SVM. I am trying to give you the introduction to SVM. I am not giving the full concept. Just you should be aware of that. You see here, this is the line. It is okay. Now, I can plot another line also. I am plotting one more line. What about this? Is it classifying or not? I can plot one more line, mouse pointer. Okay, so see here. Now in this, how many lines are there? How many possible classification lines? There may be so many, right? If we use, if we use any classical algorithms or the classification, any algorithm, it will stop when you get a line. That's it. Okay, or based on the random value taken in the weights, that will also give you the one of the line. If you change the random line, if you change the values of the initial values of the parameters, then again you will get another line. But all these lines will give you the classification line, but which we have to select. This will not be dealt by any regular classifiers. For that, we have to go for another concept that is called the hyperline, hyperplane. Hyperline and hyperplane concept. What is a hyperline? Means among all these lines, we have number of lines. Here in this diagram we have 3 lines. In these 3 lines we have to select one, right? So how can we select that? We have to calculate the distance between the line and each and every point.
It's not regarding each and every point.
Okay.
It's regarding the support vectors which we are considering.
How can you find the support vectors? First we have to fit the hyperline. Then you can go for the support vectors. First we have to fit the line, fix the line. Then we can find the support vectors. I am coming to that point. First step is, we have number of lines, 5 lines are there. You have to take first line and find the distance from all the points. Okay, and we have to find the minimum distance, right? Is it the minimum distance or maximum distance? We have to find the maximum distance, right? So we have to find the distance of each and every point with the line. We have to take all the points, all the lines, we have to consider all the lines. For all these lines, the minimum distance we are calculating, right? In that, which is having the maximum distance from all the points. First line, it is having the distance 2. Next line, it is having the distance 5. Next line, it is having the distance 1. Which is having the highest distance? One line, second line is having that. So we have to select that because it is away from all the points. It is away from all the points. Now once if you do that, once if you fix the hyperplane, then we can give some margin. You have to fit some margin. How can you fit the margin? For that, the surrounding points which are having the minimum distance, we have to collect all these points. See, we are fixing this line which are close to this. See here, we can see this here. These are the closest points, right? We can take them as the support vectors which are close to that line. They are called the support vectors. Okay? Now, based on that, we will fix a margin. The margin has to be fixed. In that margin, see here, this plus is available here. Okay? And this plus may be available here also. Now, how can we fit the model? Actually, one plus is here. You just see this. One plus is here. Then, if you take this line, it is wrong according to our formula. What is the original? What we have to get? We have to get a line like this. We have to get a line like this. So if you get this line, we may have the misclassification chances. So allow one point, and instead of taking that, take this point, take this line only. We can give some exception for that. So for that, how much we have to give the exception? For that, we have to give some margin. Instead of taking a single line, you just give some margin. If it is within the margin, it is okay, allowed. Instead of taking a single line, you take the margin. So if it is inside the margin, then allow that. Allow to misclassify, no problem. So that we will get, overall we will get the good accuracy. If you leave one or two. Right? So the fixing of the margin is also playing the important role. If you take the very large margin, it will allow everyone. If you take the narrow margin, then it doesn't allow. Again, we will have the same problem of this. So the support vector missions, this is the support vectors. Based on this, support vector classification is there. If you are increasing the dimensions, then it comes under the support vector machines. Actually, it is the line, we are talking about the line. If you increase one more dimension, it will be the plane, hyperplane. So for hyperplane, again we will have the margin. And if you increase one more dimension, it will be another shape. Another shape. Again on that, we will get one more margin. That is the kernel. We will call it as a kernel, linear kernel or radial. Radial means it will be in different shape. Right? So in the support vector missions, we have to fix the hyperplane and then hyperplane and then support vectors, margin. I am just giving the words. I cannot explain all these concepts in 10 minutes. Okay? And then kernels. Radial kernel is also there. So this is what I want to touch all the concepts in the machine learning. So I think it may be useful for you. Okay? So I want to hand over to Yunus sir to continue the mathematics.